Hi everyone, and welcome to the first XAIDA webinar after summer. Today we have Nathan Mankovic from University of Valencia that will present his work on dynamic mode decomposition with control for climate analysis, opportunities for attribution. So when you are ready, please, Nate.
Awesome. Thanks for the introduction, Maria. I'm Nate, or Nathan Mankovic. I'm a postdoc at University of Valencia. And let me know if there's anything weird with the sound. I'm in this room that has crazy echoes, so it's always a little funny, but hopefully y'all can hear me. So today I want to talk about some work I did applying dynamic mode decomposition with control to some climate data. I think my abstract I also was going to talk about a ForceSMIP project, but I think I'll just mention it here at the end. Um, all the work that I've been doing with dynamic mode decomposition with control has been joint work with Shaheen Bouabid at MIT, Peter Nowak, who's in Germany, Gerardo, Omer, Tristan, Deborah, and Gustavo, who are all at the Image and Signal Processing Lab at University of Valencia. So yeah, let's see. Okay, so first I'll be talking about modes of variability in climate. Then I'll talk about climate and climate scenarios. Next, I'll introduce dynamic mode decomposition with control. We'll talk about some experiments, and I will conclude. A caveat here, I'm not a climate scientist. I'm newer to this stuff. So please, anyone here with absolute expertise in climate, feel free to correct me or anything, any comments are certainly helpful. So modes of variability in climate, how do I understand them and what are some examples? So in general, I think of modes of variability as these spatial patterns that vary over time. And they affect global weather patterns in other parts of the world via these things called teleconnections. So this is a figure on the right from some work by Jakob Runge. And an example of this is the El Niño Southern Oscillation, which is a pattern generally found in sea surface temperatures, but is sort of part of a larger linkage between different climatological systems. But these are the patterns that you normally see. You see this El Niño pattern, which is warming in the Pacific, and the La Nina pattern, which is more cooling, and you oscillate between these two patterns. And so it's normally called the El Niño Southern Oscillation, or ENSO. This is a super common mode of variability. And this ENSO affects rainfall throughout the world. So during the El Niño times, when you have warming off the coast of South America, in the tropics, you see the El Niño pattern, and this causes wet and dry periods in different places in the world, which can in fact affect extreme events. And with the La Nina pattern, you see different wet and dry patterns throughout the world, and more or less opposite, but not quite if you kind of glance at both of these. And like I said, there's an oscillation between these two sea surface temperature patterns, and it's about every 2 to 7 years that you see this oscillation between warming and cooling. And so these rainfall events, these wetter or drier conditions in different parts of the world can come in more of the form of extreme events such as droughts or monsoons and things like that. So these are modes of variability, and ENSO is one example. So we also know that ENSO, its oscillation and its intensity are affected by climate change. So this is something that's been known before. So, okay, now we have an example of a mode of variability. Now let's recap, or let's state our objectives here of my study. My goal is to detect modes of variability like ENSO and other spatial patterns. And then I'm going to determine their change over climate scenarios. So I haven't introduced a climate scenario yet, but we'll get into that in a second. here we are. So climate scenarios come with this data set that we'll be working with. The data set is called Climate Bench. Forgive me, I don't apparently have the citation on this slide, but I think it's in the next one. This is a data set that came out, I think in 2020, 2021. And essentially it consists of different climate scenarios, and we call these shared socioeconomic pathways. What are these things? These are simulations of future climatological variables under different emissions patterns. So let's look at an example. So, this is one climatological variable, surface air temperature. And Climate Bench has this variable at approximately like a 2-degree gridded resolution globally. And here I just plot the global mean, but really the data I'll be working with is like an image where each pixel represents a surface air temperature at a location. And you have these gridded surface air temperatures for different climatological or different climate scenarios or shared socioeconomic pathways, meaning under different emissions conditions. So SSP is the lowest emissions scenario. And if you look at the temperature over time, you see that the global mean surface air temperature doesn't increase too much in the later years. And these scenarios really start at the year 2014. And then SSP 245 changes less or changes more because it's a higher emission scenario. SSP 330 changes even more, higher emission scenario, and SSP 585 changes the most. And we break down the emissions in this data set into different modalities. You have carbon dioxide, I believe this is carbon monoxide, sulfur dioxide, and black carbon. And what we do actually is we, from the Climate Bench data set, which has some graded information for these different modalities, we actually compute a radiative forcing measurement. And here we're just visualizing the radiative forcing for each of these scenarios. So you can see the magnitude of the radiative forcing from each of these agents is higher under higher emission scenarios and lower under lower emission scenarios. So yeah, this is a climate scenario is, for example, SSP 585 or shared socioeconomic pathway 585, where you have, and then you can look at certain variables from these scenarios like surface air temperature and and it also comes with the radiative forcing information. So in terms of representing these data, we use X's to represent the surface air temperature and Y to represent the radiative forcing from emissions. Let's get into it a little bit more carefully. So this is an example of SSP 585. What I'm plotting here is actually the evolution over time in the blue box of SSP 585. And then the average, the global average at each time point is exactly what's plotted here. And so you have high emissions scenarios and low emission scenarios. We have historical data and the scenario data. And we encode X1 is exactly the global surface air temperature flattened at time 1, which might be like 1850, for example. You have your radiative forcing information, which we've already gone through, and we're computing radiative forcing from the Climate Bench data. So yeah, we have 4 emission scenarios, we have radiative forcing, and we're working with surface air temperature. So our objective is to detect modes of variability and determine how they change over different climate scenarios. So there are classical methods for detecting modes of variability, such as principal component analysis. And also people have used linear inverse models or dynamic mode decomposition, which are essentially the same thing. And these are certainly 2 things you could use with these data, but we want to include this radiative forcing information, which is obviously significant in terms of the change of the global surface air temperature. So in order to include forcing information into our model, we choose to use dynamic mode decomposition with control. So what is dynamic mode decomposition with control? Maybe best to kind of give an overview relating it to principal component analysis and dynamic mode decomposition. So first off, I want to name some of our variables here. The temperature, the gridded temperature at time t. So this is a sort of, if you take the image of the entire globe at time t, where each pixel represents a surface air temperature, you flatten that, vectorize it, that gives you your x. The radiative forcing at times t through t minus 29, so these are the last 30 years of radiative forcing, are stored in this variable y. So we choose to do this sort of time delay for the forcing because we know that some forcing agents don't have an immediate effect on surface air temperature. It takes more than 1 year for agents such as carbon dioxide to affect global surface air temperature. And then, yeah, the temperature at time t plus 1, we'll just call x prime. And so let's go through each one of these models. So again, I'm not as rigorous as I could be, but to be hand wavy about it, the PCA model essentially says your temperature at time t can be approximated by projecting your temperature at time t onto a lower dimensional space. And that's what this is. So this is just like saying that, yeah, the temperature at time t isn't that complicated. So we model it by projecting it onto a lower dimensional space. Dynamic mode decomposition has some time series going on in its model where you say that the temperature at time t plus 1 is a linear function of the temperature at time t. So you kind of have this sort of at each year, you're saying the temperature at time t is, yeah, if you map it linearly, you get the temperature at time t plus 1. But this doesn't, neither DMD nor PCA include the forcing information. So we include B here to include the forcing information. So now we say the temperature at time t plus 1 is a linear function of the temperature at time t plus the temperature, the radiative forcing in the last 30 years. So you get modes of variability out of these things. The modes from PCA are the directions of maximum variance, which come from U. The modes from DMD come from A, and the modes of variability from DMDc come from A and the forcing, which you can extract from B. So you get modes of variability from A and B from DMDc. You also get eigenvalues from PCA, which tells you how much variance your modes explain in the data. Your eigenvalues from DMD tell you the evolution of the modes over time. And dynamic mode decomposition with control, you also get the same eigenvalues as DMD associated with A. PCA is a variance-based analysis. DMD is a linear dynamics-based analysis. And DMDc is also linear dynamics-based analysis, but you're adding in this control, the control being this BY, this forcing information. So let's zoom in on DMDc a little bit and look at how it works. So this model is from Proctor et al. In 2016, so it's been used quite a bit. But essentially, like I said, the next year of SAT is approximately a linear function of the last year of SAT plus the last 30 years of radiative forcing. That's the model. And so what we're going to do is decompose A and B to get what we call the autoregressive component from A. So these are modes of variability that come from the last year of temperature affecting the next year of temperature. And then we get modes of variability that encapsulate sort of the emissions contribution from B. Okay, so let's talk about the autoregressive component. DMDc outputs an approximation of A. And when you do the eigen decomposition of this approximation, you get these spatial patterns, which are called dynamic modes, and you get the temporal patterns associated with each one, which are like the eigenvalues. So essentially, each dynamic mode has some sort of oscillation pattern over time, which comes from these eigenvalues, lambda. Yeah, we'll leave it at that. And the emissions contribution from DMDc comes from an approximation of B, and I call it F for like the forcing contribution, the linear forcing contribution. And this is an approximation of B. And essentially, because of the way we structure Y in this time delay embedded sort of framework with the last 30 years of forcing, you can actually decompose F into blocks. And this was my best way to visualize it. I'm sure there are better ways, but essentially you can think of F as one big matrix, and you can decompose its columns. Like the first column is the spatial pattern associated with the contribution of carbon dioxide from 1 year before the predicted year. And then you can look at carbon monoxide, sulfur dioxide, and black carbon. So if you look at the product of the corresponding entries of Y and these entries in F, you will get the actual contribution of that emissions agent that many years in the past to the future year. And this can be useful potentially for attributing emissions and modalities to local temperature changes. So yeah, so kind of two different decompositions. One, the decomposition of A, which is an eigen decomposition, and the decomposition of F, which is really just looking at its entries and what they correspond to physically. So to summarize this, what we do is we take a climate scenario. We have surface air temperature as our x's. We have radiative forcing as our y's. We run dynamic mode decomposition with control, and we plot the scaled modes of A and the entries of B. In fact, we use the entries of B. We plot the entries of Fy, which is the approximation of B times Y. We plot this here, and this gives us modes of variability, which we can analyze for each scenario. So we can do this. What we do is we do this for each climate scenario, SSP 126, 245, and so on. So the pipeline is send in a flattened SSP time series. So this includes surface air temperature and radiative forcing, run DMDc. We choose to extract 5 modes of variability to give us these spatial temporal plots, and we compare these across the shared socioeconomic pathways. So our goal now is the same as it was at the beginning, but now in order to do this, we're going to detect and analyze the autoregressive component and the emissions contributions. Okay, so now we get into experimental results. And man, I've been moving a little fast, so I'll try to slow down while we discuss these results. So yeah, here we're looking at the global warming mode. So what ends up happening here is that you have 2 scaled dynamic modes of A. So we plot the dynamic modes of A, and then we scale them. I didn't want to get into the details of scaled dynamic modes for the sake of this presentation, but this is essentially a correction of the sign of the dynamic modes in order to be able to visualize them correctly. Like, for example, when you run PCA and you get EOFs, there's some sort of sign ambiguity, and you kind of just have to look at the pattern that you get, and then you have to correct for the sign ambiguity on your own. Whereas with dynamic mode decomposition and dynamic mode decomposition with control, there's maybe more of a principled way to correct the sign ambiguity. And we have 2 sort of dynamic modes of A, one which is more of a warming mode and one which is more of a cooling mode. And when you add them, you kind of see more consistent patterns across the climate scenario. So we chose to add them together. Each of these plots is a spatial pattern, which is the sum of the 2 scaled modes. And on the right side, what you're seeing is the mean of I'm going to say this is essentially the row sums here across. I always forget latitudinal profile or longitudinal profile, but you're seeing the mean of the entries for each row here. And yeah, now let's start talking about the patterns that pop out. So the first pattern that we see is landmass warming, especially in the northern hemisphere. And this is consistent across all scenarios. And in general, too, we see higher warming in the higher forcing scenarios as well. So this blue line here corresponds to the highest forcing scenario, and it's certainly above these other lines. So on average, we're seeing higher warming in the northern hemisphere for higher forcing scenarios, especially on land. And we also see this weakening of the North Atlantic warming hole as we look into higher and higher forcing scenarios. So I think this is where I try to play climate scientist, but this is associated with the North Atlantic Oscillation and the Atlantic Mercadial overturning. And this has been seen, I think, in previous work to weaken. The North Atlantic warming hole weakens in higher forcing scenarios. And this, I think, is somehow related to the slowing down of some of these essential circulations, such as AMOC. Yeah, so we see this pattern. It corresponds to this cooling in the Northern Pacific or the Northern Atlantic. Oof. Okay, and we also see this equatorial Pacific warming. And here there's not much of a pattern across different climate scenarios. I think the main thing you see is maybe a weakening of the equatorial Pacific warming in SSP 370, which is something that you might expect because this is a higher aerosol scenario. So the aerosols might be cooling things a little bit more in that region. And finally, there's this pattern that's less common, this cooling in the South Atlantic. And if anyone has a nice explanation for this, I'd be excited to hear. But this is a pattern that shows up in the warming mode. So to summarize, with this warming mode, we see higher warming on land and for higher emissions scenarios. We see a weakening of this North Atlantic warming hole in higher emission scenarios. We see a warming pattern in the equatorial Pacific and some South Atlantic cooling. So yeah, one thing I didn't discuss here is that each of these patterns, this comes from A, right? This is part of the autoregressive component. This also comes with an oscillation over time with the associated eigenvalue to the dynamic modes. And this warming pattern, one of the reasons we're calling it sort of a warming pattern is that it's associated with an eigenvalue that's all real, which indicates no oscillation over time. So this is like a pattern that doesn't oscillate, and it's more or less consistent across time. Whereas there are oscillatory patterns like the El Niño Southern Oscillation, and we call this maybe the ENSO mode, which is maybe a little bold, but we'll see why in a moment. So in this mode, I think this is the sum of two scale dynamic modes of our approximation of the matrix A. And these are associated with eigenvalues which indicate some oscillation over time. In addition, in this mode, you see this warming pattern in the Pacific off the coast of South America. And this is exactly this sort of El Nino type pattern in all climate scenarios, except for the highest forcing climate scenario, where you see something that looks more like cooling. But these spatial patterns are associated with temporal patterns through the eigenvalues, so we can actually evolve them over time. And when we do that to SSP 585, and we evolve it 1 year, we actually see this warming show up in the Pacific. So, okay, we're getting this type of El Nino type Pacific warming pattern in all of these oscillatory modes and these oscillatory modes across all emission scenarios. So this looks something like ENSO. Now we're curious about the oscillation of these patterns. And so we can analyze the eigenvalues and look at the oscillation patterns over time. And I think, honestly, maybe it's better to just give the period of oscillation here, but instead of that, I am actually plotting sort of how the eigenvalues oscillate over the years. And the pattern that we generally see is that we see faster ENSO oscillation in higher emission scenarios. So we're seeing, we're seeing lower period and higher frequency for higher emission scenarios, which is something that has been seen in other literature as well. The one outlier here is this SSP 245, which doesn't follow the pattern of increased ENSO oscillation for higher emission scenarios. But other than that, we're seeing higher ENSO oscillation, which I guess could lead to higher frequencies of extreme events or higher frequencies in El Nino, for example, which could lead to extreme events. I'm certainly stretching things here quite a lot, but this is what we found. Now let's look at the C part, the control part, the forcing contribution from dynamic mode decomposition with control. This is something, right, that this is part of the reason we're using DMDc, right? We could have used dynamic mode decomposition or principal component analysis, but these don't include the essential forcing information from the radiative forcing that you get in Climate Bench. So we choose to use dynamic mode decomposition with control. And so the first thing that we do is we plot all of BY for some years and take a look at the patterns. So we approximate B by F, so we're plotting Fy, and this is the forcing contribution to the next year. And we see some nice patterns. Firstly, we see polar amplification, so warming in the northern hemisphere near the poles. And this is consistent across all scenarios and is highest in SSP 585. And we also see some equatorial Pacific cooling, which is also something that we've seen in literature in all scenarios except for SSP 126. But this is all well and good, but in fact, the magnitude of these patterns is actually quite low in comparison to the magnitude of the dynamic modes of A. And so this indicates that the DMDc model isn't fully capturing the contribution of radiative forcing. And I think we'll have more on that in the next few slides, but yeah. So let's plot, do some more plots of this emissions contribution. So if we plot the emissions contribution for each year and look at it across different scenarios, we see for the future emission scenarios, we see on average that higher emission scenarios have higher forcing contribution, which is expected, but again, the magnitude is quite low. Then we sum the entries of Fy across scenarios, and what we're doing now is we're looking to see sort of this time delayed effect of the emissions contribution. And we see that as we look further into the past, we see a higher effect or a higher contribution from the radiative forcing. And then now we're doing sort of this decomposition of F even further. So the previous plot was looking at the average of the entries of year 1, year 2, up to year 30. But now we're going to look at actual entries in each of these corresponding to each of these emissions modalities. So here we'll look at the average of or not the average, we're actually going to look at the entries for just CO2, then the entries just corresponding to CH4, just SO4, and just BC. So this is where things start to look not so good. I think we're not seeing, so first off, on these plots, these are the plots of sort of the distribution of pixel values for each emissions modality under different climate scenarios. And the whiskers on these blocks are not like, 1 or 2 standard deviations from the mean. I'm just using the whiskers to encapsulate all of the pixel values. So this is just incorporating, the whiskers incorporate all of the pixel values, which is kind of a strange thing to do, but I chose to do that. And yeah, I think this is where things start to fall apart. I said the magnitude of the emissions are small, but we expect to see general warming for CO2. What should it be? Then warming for CH4 and cooling for SO2 and cooling for black carbon, and that should be moderately consistent across all scenarios. And it should be like that at least on average for pixel values, but this is not what we're seeing here. And in fact, most of the emissions contribution here is coming in carbon dioxide. So we're not actually capturing the effect of aerosols in the way that we want to. So not only are we seeing high warming from carbon-based emissions and cooling from aerosols, we're also not seeing proportionally the correct effect from the aerosol emissions. But we are seeing a higher impact from carbon-based emissions, so that's at least something. And this is sort of a slide to summarize what we see from these emissions contributions. So the good are that we're seeing higher warming in higher emission scenarios. We're seeing a higher forcing contribution as we look further into the past, and we're seeing a higher impact from carbon-based emissions. The bad, however, is we see small contributions from CH4 and aerosols, and we see little to no cooling from aerosols. So something I wanted to do is kind of double click on the aerosols emissions and look just at sulfur dioxide and look at it on land masses. And so when we do that, now what I'm plotting here is the pixel value distributions. And this time the whiskers, I think, are the first quartile or whatever is standard actually. When you use Python to plot these things are seaborn. Yeah, so each color corresponds to a different emission scenario. And then each of these box plots corresponds to a different region, landmass. And something that we do see is cooling in SSP 585 from sulfur dioxide, although the magnitude is super small. At least we're seeing some cooling on land masses. But in other emission scenarios, we're still not seeing the cooling that we want to see. So to conclude, and I realized I went a little fast. So we had these objectives. We wanted to detect modes of variability, and we wanted to determine their change over climate scenarios. So we detected sort of 2 versions of the first forced response, or one being sort of this dynamic version, the forced response that changes over time, like the oscillation of ENSO. We saw that ENSO oscillates in the ENSO mode oscillated higher in higher scenarios, had a higher frequency of oscillation in higher scenarios. And we also saw parts of the thermodynamic forced response, such as the polar amplification in the emissions contribution. We also determined the change of some of these modes across different climate scenarios. We saw, like I said, increased ENSO oscillation and increased polar amplification in higher emission scenarios, among other things. So there are other applications of this project, namely to ForceSMIP. Since I have a little bit of extra time, I'll try to take a couple minutes and explain this project. So essentially, ForceSMIP is a project where you try to disentangle the internal variability and the forced response in different climate variables, from different climate variables. And the goal of ForceSMIP is specifically to predict the forced response. And I'll talk about that in 1 second. I have a nice plot and a couple of mentions. But yeah, essentially we used dynamic mode decomposition to predict the forced response from various climatological variables. And this is a hackathon that's like global. And yeah, DMDc was sort of middle of the road, but I used it in a bit of a naive way to predict the forced response. So that was good. And some of the future work, I guess, with dynamic mode decomposition with control and similar methods are to improve detection of the aerosol effects on surface air temperature, specifically by maybe adding causal or physical models, or maybe incorporating some nonlinear formulation of dynamic mode decomposition with control. So maybe I will actually just end it here. And I can talk more about ForceSMIP if someone's interested. Thanks.
Thank you, Nate, for your presentation. So let's move on to the turn of questions. Just unmute yourself if you have any question, use the chat or react to raise your hand and we will give you the turn.
I'm happy to talk more and advertise the ForceSMIP project really quick if there are no further questions.
Yeah, sure. Go ahead.
Okay. So this is like a hackathon, and essentially given some sort of climate variable like sea surface temperature or precipitation, the idea is that these signals, these spatial patterns which vary over time, can be separated into two parts: their internal variability and the forced response. The dumbest way to think about this, I stole this from the internet, is the red curve might be like 1 pixel value, which slowly increases over time and has some oscillation. And the internal variability would be this sort of oscillation, and the forcing would be this sort of linear slow increase over time. Super simple, but the idea now with ForceSMIP is that you take these large ensemble climate models, and we take 5 of them and 8 different climatological fields like sea surface temperature, precipitation, geopotential height, and more. And these data have monthly resolution. And so one large ensemble is one climate model or one model of the Earth. And for each one of these models, you're going to have different you'll have different members of the model, which are essentially different simulations where this model has been run with a different initial condition. And these things change over time. And the idea is that when you average all the members for one large ensemble, you get an estimation of the forced response. This is just the way these people decided to set it up. And the goal for the hackathon is essentially given one member can you predict the estimated force response from one ensemble member? And can you have a method that works for different fields and for different climate models? So it's kind of, yeah, that's kind of the setup. And there's a website that you can go to if you want to submit any method. I think if you just Google ForceSMIP, it's there. If I end up sharing my slides at the end, you can click on the link in my slides. I think it's right here. You can click on this link and you'll go to the website and you can submit. I think the next submissions, I think, are this winter. And yeah, I guess what I ended up doing was I used dynamic mode decomposition with control in one way or another to predict the force response for these different variables. And yeah, it's a cool project. A lot of people are participating and it's pretty international. So yeah.
Okay, cool. So I think if there are no more questions, I think maybe we can finish here. So thank you very much for your presentation, Nate, and thank you everyone for coming to this seminar, and see you on to the next one.